Okay, welcome everyone to the San Diego Kotlin user group. We have Jack today from 2B. He's going to be presenting on strong typing. And take it away, Jack. Thanks for presenting today.
Yeah, no, thank you, Ian. So yeah, strong typing and the errors it prevents is what I'm here to talk about. But before we get into that, I would actually like to do a quick poll of the audience, just to see um, what languages. I guess what is your preferred programming language is how I would put it. This is a talk I did in a different audience. Here, I imagine it will be a lot of Kotlin. So I actually updated the poll a little bit so that you can pick up to 3 languages. So I'm assuming Kotlin is going to be number 1, and then we can do number 2 and number 3 for a little bit of variety. And so just type it into chat. So for instance, I'm going to do like Perl and JavaScript. No, I'm just kidding. So Kotlin, Scala, and Elm are my 3. And if we'll see, we'll give it a few seconds. Oh, and if you do more than 3, only your last 3 is going to count. So you might want to keep the last 3. Yeah, because we are limiting only to 3. Oh, we actually have more Java than Kotlin today. But okay, but I think that's because a bunch of you had Kotlin too early. Okay, cool. So a lot of Java, a lot of Kotlin, not surprising. Actually, a fair bit of TypeScript as well. And I'll be talking about TypeScript. I'll be talking about common languages. So of the languages here, I'll be talking about Swift, Python, TypeScript, Kotlin, and Go. So let's get that. This is interesting. Let's get into. Okay, and okay, I did this also if there is TypeScript and JavaScript, kind of just to get a sense for people because I kind of see JavaScript as a less strongly typed TypeScript or vice versa. So this is kind of just to give a sense of the audience like preference towards strong or weak typing. So it looks like it's more strong typing related, at least amongst the JavaScript and TypeScript folks. Let's get started. So what does strongly typed mean, right? What's strong typing? There's really no formal definition for the term. If you look in Wikipedia, it describes it as, languages can be classified colloquially, as it says, as either it's strongly typed or weakly typed, and also called loosely typed. And read further down, it's like generally it's a strongly typed language has stricter typing rules at compile time, which implies that errors and exceptions are more likely to happen during compilation. So the compiler is more likely to catch errors. So if you only take one thing away from the talk, just know that a strongly typed language is more likely to catch errors during compilation or during type checking. Basically, think of it before your code runs, it's catching errors. And for the purpose of my talk, the definition is basically that, right? Like the strength of the type system describes its ability to prevent runtime errors. So the stronger the type system, the more kinds of errors are detected during type checking, and a fewer exceptions are still possible during runtime. Like I said, Elm promises no runtime exceptions, so it's trying to be really strongly typed there. Also, I want to mention, because I think this is something that people sometimes confuse, is strongly typed does not mean statically typed. So statically typed just means a language is compiled. But a language can be compiled, but the compiler isn't doing very much for you. And so it can be statically typed and relatively weakly typed. On the other hand, these days with languages with optional static typing with things like Python with typing and Ruby with sorbet, you can actually have dynamically typed languages that are in fact fairly strongly typed. And we'll show examples of this. Now you guys might be skeptical with that explanation, right? Like how can a compiler catch errors? And there are definitely classes of errors that no compiler will ever catch, or at least with current technology, right? Like so infinite loops in general, if a program will terminate, that's a halting problem. So that's kind of a known thing that cannot be determined at compile time. Stack overflows, out of memory errors, so like basically resource exhaustion problems, not going to be caught at compile time. Arithmetic errors technically possible, but in general, division by zero, overflows or underflows are not being caught at compile time. Rust actually has an option to do, for instance, checked add that basically says if your addition overflows, you actually have to handle it. But by default, it's usually not the case. And I think the last one I would say is I guess the obvious one, where business requirements coming from a human, like a static type checker, cannot possibly catch it. Like if your product manager says, hey, I want a mobile app that has a blue background, and you give it a red background, type checker isn't going to stop that from happening. So let's talk about errors that a type checker can catch. I'll go through this in detail, but really the whole talk is going to be about going into some of these things in detail. So I won't go into too much detail here. The first two, memory leaks and buffer overflows. I'm not going to go into detail, but the reason I'm not going into detail is the 5 languages we're going to cover today. All of them does this. This is kind of like, unless you're doing C, C++, you really, with modern languages, do not have to worry about it, because memory leak, most languages come with a garbage collector. If you're in Rust, there's the borrow checker model. Buffer overflow is when you've got an array, like in C, you can declare an array of size 10, and then you can get the 10,000th element, and it will return you a value, which is just whatever happens to be there. You can even write to it, which is how buffer overflows happen. Modern languages don't allow that. Type mismatch. If you have a function that takes an integer and you try to pass it a string, does it let you? Null pointer dereference, null pointer exceptions. Basically, I think what Sandhu was talking about earlier. Out of bounds array access. Again, so I say now that modern languages will bounce check your arrays, but what happens if you try to access a value that's outside of the array length? Do you get a runtime exception or not? Type conversion failure, this is typecasting. So, is typecasting safe in the language? Unhandled recoverable error. We'll talk about that in more detail. Exhaustive matches as well. We'll talk about it in more detail. State data corruption, and is basically, let's say you've got a counter, it has a value that should never be negative. Will it become negative? If it does become negative, is there, how hard is it to figure out what went wrong? And finally, data race is another one that I will not be covering today. However, it is on this list because a type checker can actually prevent it with more like really modern languages, like Rust and Pony are 2 examples that actually, if it compiles, it promises that it is data race free. However, we are not talking about it today because none of the languages we are talking about today will prevent data race errors. So type system properties, again, these are really just the properties. It kind of maps to the classes of errors we were talking about before. So type safety prevents, type mismatch errors. Null safety prevents null dereference errors, etc. Again, these will be the 8 items that we will be going into in great detail, covering 5 languages that are in common use. Really, I say common use. It is the 5 languages that I used at my last job, but it is fairly common languages. So these are Go, Python, TypeScript, Kotlin, and Swift. And the way I'm doing this analysis is for each of these 5 languages and for each of the 8 properties earlier. So basically, there'll be think of it as a matrix of 40 items. Though I'll breeze through some of the 40. I will basically determine upper bound and a lower bound score. So let's start with a simple example. So Kotlin and type safety. Is Kotlin type safe? It is. It's built into the language. So Kotlin has a type safety score upper bound of 1. With Kotlin, right? Like if you define a function that takes an int and you try to pass in a string, it's pretty much impossible to defeat. In theory, you could like use an any type and do typecasting, but you basically are putting a lot of effort into it. So for all purposes and intents and purposes, I consider Kotlin's lower bound for type safety 1 as well. So it has an upper bound and lower bound of 1. Python, on the other hand, also has type safety built in if you consider typing that came in Python 3.7. However, its lower bound is 0 because with Python, by design, typing is optional. The idea is you use it if you want to. So it's actually fairly easy, and we'll show you how to accidentally not use it. So again, it has a lower bound of 0 and a bound of 1. I know this might sound a little bit vague right now. Hopefully, as we go into the talk, it will become clearer. So first topic, type safety. Oh, by the way, any questions so far on what we're talking about today? Cool. So type safety is, the most fundamental aspect of strong typing. So I think in some cases, in some people's minds, like type safety is strong typing, but I think I'm here to show that strong typing goes beyond type safety. But type safety, I define basically as all data values have distinct types, and function inputs and outputs also have types, right? So function parameters and return types, they all have types. So a type safe language ensures that types match across the entire program. So here's an example. Let's start with Go. So Go is type safe. So this is how you define a function in Go, right? This is a multiply function. It takes two floating point parameters and returns a floating point value. And if you pass in two numbers, it is valid. It returns and assign it to a floating point variable. It is valid. The code compiles. It runs just fine. But if you try to pass in values that are not numbers, like a string and a Boolean, the compiler catches it, so you do not even get running code. If you were to try and defeat this because you say, no, I do not want your help type system, and you basically say, and again, Go's version of any is the empty interface. So, and this is Go 1.17. Go 1.18 actually introduced the any keyword, but basically, if you try to say, hey, I just want to be able to pass in whatever I want, the Go compiler actually won't let you do that, because you're saying now, hey, you're trying to multiply two things that are not numbers. I cannot do that. So really, if you really want to defeat the type system, you have to jump through a bunch of hoops, right? You have to make it an any, and then you have to first see if it can be casted to a float 64. And only if it does, and if it cannot, it actually by default, Go defaults it to what they call their zero value. So this becomes zeros, and multiply will return 0. In this case, like when you pass in a string and a Boolean, it will return 0. Yeah, so that's Go. Strong type safe. Python can be type safe as well. So if you're using Python with the typing, it will be, this is the equivalent in Python. Multiply function takes two floats, returns a float. You give it two numbers, it's cool with it. If you don't give it two numbers though, Python is doing something slightly interesting. It complains about the string. It actually isn't complaining about the Boolean. And the reason for this is in Python, Booleans are a subtype of integer, and integer can be passed into a float. So that's something to be aware of in Python. But however, because Python is optional by design, what that means is you can completely leave out the type information. And this is, in fact, if anything, this is more what people think of as Python. Like this is classical Python. And the type checker, if you run the type checker, it'll be totally cool with this. But if you run the program, you are going to get a runtime error because you're trying to multiply. This error basically says you're multiplying a sequence, a string is a sequence, by a non-int. So you can actually, in Python, multiply a string by a number where it just repeats a string. But when you cannot multiply two strings, is what this is saying. So more on Python though, right? Note that Python typing is added on later, it's optional. And they are really just hints. As in, let's say we take the program from the last slide and we correct it. So that it's basically the same program, except I'm passing it two numbers as I should be. But I also remove the type information. You'll notice there's no type information. If I run it, it runs just fine. It gives me a number. If I intentionally give it bad type information though, like I say, okay, these are strings, even though I know they're not. And I run the type checker will say, well, you cannot do this. You cannot multiply two strings, and you cannot pass numbers in as strings. So the type checker will actually complain. But if you say, thank you, type checker, I'm going to run the program anyway, the program actually runs correctly because the Python runtime actually ignores type hints. Type hints are just there to, for a couple of reasons. One, it is for tools like PyCharm and VS Code so that you can see errors there. And also, if you incorporate it into your CI/CD system, there are command line type checkers that you can use to basically, and you should do this, right? Make sure that your code type checks before it gets published, deployed, whatever. And the three major typing compatible type checkers I'm familiar with are MyPy from Dropbox, PyWrite from Microsoft, and Pyre from Facebook. Of these three, I've been looking at these three. I would say if you need to pick one, I would go with PyWrite. It is from Microsoft. It does the most for you. It's the most strongly typed. It's also the slowest as a result because it has more work to do. But yeah, that's the one I would use. TypeScript, I'm going to breeze through the rest a little bit because I think they're going to seem familiar. But TypeScript, again, same thing, very similar to Python, as in it has static type, it has type safety, takes in two numbers, returns a number. And if you try to give it the bad values, it will prevent it. However, similar to Python, typing is optional. And in this case, the reason they did it this way is because it's for gradual transition from JavaScript. They want to be, they want to be compatible with JavaScript. So they basically do not want to force too much typing into it. So you can use any, for instance, in this case, this will compile just fine, but it will fail at runtime. Or you can drop type information altogether. In this case, this is basically just JavaScript. It will just take JavaScript and will compile it just fine. However, this actually will not compile if you are in strict mode. If you run TSC, the TypeScript compiler, in strict mode, this will not compile. But if you're not in strict mode, this is valid. My biggest problem with TypeScript, though, is, again, it's related to backward compatibility with JavaScript. Code like this, so on the element, there's an onClose property that has this signature, right? It's either null is okay, but if it's not null, it says it's supposed to be a function from two parameters to any. However, if I give it a function from no parameters to nothing, this actually compiles anyway. And this has led to a bug that someone told me about, where they accidentally pass in window.close to the element.onClose. And when they click on the element, it closes the window instead of running some code that they were supposed to run. So as far as I know, no other language, at least no other language on this list allows this. But I think TypeScript has to because JavaScript allows this. Kotlin is type safe. I think you guys are familiar with this. It's the most succinct of the languages we're covering today. So multiply takes two numbers, multiply them, pass in the wrong values, it doesn't like it. If you just do any, same thing, you cannot multiply two any's. So you have to basically check the type. Again, you have to do a lot of work to bypass type safety in Kotlin. Swift, very similar to Kotlin. I'm just showing you, syntactically how they're different, but basically same guarantees being offered. Doesn't like it. And any doesn't multiply. You have to, and this is how you do typecasting in Swift, which we'll go into later. One thing I want to point out for Swift, which actually applies to Kotlin as well, is you have to change, again, you have to type check to make sure that the nums are doubles. And if they are not, you return nil. But because now you're making the return type nilable, you actually have to add a question mark to the double here, which you have to do for Kotlin as well. So let's talk about the scoring earlier. So I said earlier that Kotlin has a lower bound of 1 and an upper bound of 1. So that's how I'm visualizing it here. Go and Swift is the same. Python, like I said, type safety is optional, so it's a lower bound of 0, but an upper bound of 1. TypeScript, because of its weird JavaScript compatibility thing, I'm just giving it a half for upper bound, but lower bound of 0. And I want to mention here that Python and TypeScript, you're going to find that the lower bound is going to be 0 all the way to the end. And this is by design, right? Because typing is optional for these languages. And I would say, I guess, from a strong typing perspective, the ideal language would be lower bound of 8 and upper bound of 8. But as we go through the slides, you'll see where we end up at. Any questions so far? Cool. I'll keep going. I know I covered the last section in a fair bit of detail. To make sure we have time to cover everything, I'm probably going to skip through some of this because, as you might guess, some of this gets fairly repetitive, especially like Kotlin and Swift are fairly similar languages, and TypeScript and Python not exactly similar, but they share a lot of similar things. So I will maybe breeze through some of those a little bit. So let's talk about null safety. Again, Kotlin folks, I think you guys are fairly familiar with what this is, but basically a null safe language makes it impossible to dereference null pointers. Again, we're talking if we're writing pure Kotlin, for instance, or pure Swift. If you have to interrupt with Objective-C, with Java, some of these guarantees are harder to enforce. But the way this is implemented in the languages that do it, all four that does it, in fact, is basically divide pointers into nullable pointers or non-nullable pointers. So if a pointer is nullable, you have to check it before you access it. On the other hand, if you declare a pointer as non-nullable, though, then you have to always assign it a non-null value. However, you can access it without null checking. So Go is not null safe. So if you look at this program, so a star string, this is similar to C, is a pointer to a string. And we are clearly assigning nil to it. But we are trying to print it by dereferencing the variable. And the Go compiler, like even something this obvious that any you would think a static analysis tool should be able to find, the Go compiler allows it. No static analysis tool, as far as I know, in Go would actually catch this, and it would panic when you try to run it. That's really all I have to say on the Go side. So Python, I'll go into detail here, but like I said, all four languages does this very similarly. When you declare a variable and you say it's a string, in Python, that means it is a string. It is not null. It cannot be null, or in Python's case, none is Python's version of null. And as a result, you can just call text.upper without checking to see if it's null. If you attempt to assign none to this variable, the type checker will not allow it because you're saying it's a string. The type checker says a string cannot be none. If you want to assign, if you want this to pass, you basically need to make it in Python, and there are other syntax in Python to do something similar, but optional of string is one way of doing it. And this basically says it's a text. It could be a string, but it could also be none. But now this code, the next line does not compile because the Python type checker is saying, wait, hold on. Text could be a string, yes, but it could also be a none. And if it's none, I do not know what to do with this line. So you need to make sure it's not none before you execute it. And you do that, again, Kotlin is similar. If text is not none, then you can do it. Right? Like I said, in Python, there are multiple ways of declaring something as optional. So optional is really just syntactic sugar, really a type alias for a union of string or none. And starting Python 3.10, instead of union of string or none, you can also do string pipe none, which is basically the same thing. And this is how TypeScript does it as well. So TypeScript, I'm going to breeze through, but conceptually really similar. Variable, if it's declared string, cannot be null. If you try to set it to null, it does not compile. If you make it string or null, which is how you do it in TypeScript, now this line compiles, but you cannot call to uppercase on it without first checking for null. So you have to check for null. First, I did it as a one-liner here. So if text is not equal null, then it's okay to do text.to_uppercase, and this will compile. TypeScript, I also want to just mention, offers syntactic sugar to simplify null value access. So I think you guys will be familiar with this, but there's the question mark dot operator, which basically says if text is null, the whole expression evaluates to null. Otherwise, just call the method on it and it's whatever gets returned. And then the question mark basically says if the thing on the left is null, use the value on the right side. Otherwise, just use the value on the left. Kotlin, very similar to TypeScript. Like I said, variable. In this case, I'm just showing you the nullable version right away. So string question mark, because of the question mark, it can be null. And you have to check for null before you call text.uppercase on it. I'm not showing you the versions that fail, but basically, if this question mark wasn't here, it wouldn't compile. Similarly, if you're not doing the if check, this will not compile if it's nullable. And like TypeScript, there's syntactic sugar. And the only difference between Kotlin and TypeScript is instead of question mark, you've got this Elvis operator, question mark, colon. But otherwise, it behaves the same. The downside with Kotlin, though, is it actually has unsafe versions. So I know we were talking about Java interrupt before, but Kotlin also has this bang bang dot, which is basically say, I know text can be null, but trust me, I know what I'm doing. I want to call uppercase on it. And this particular example will throw a null pointer exception at runtime. Another thing that I'm not showing here is late init. So you can actually declare a variable as late init, which basically means that at some point it's going to get initialized and it will not be null, and it will never be null forevermore. But between now and then, there's a brief period that it could be null. And if you try to use this variable, you could get a null pointer exception, or you could get an exception. I think they make it different. Swift, very similar to Kotlin, syntactically a little bit different, but in terms of the features it provides, a string is, if it has question mark, it means it can be null. If it can be null, or nil in Swift's case, you have to check for nil before you try to use it. Swift's sugared versions, this is actually identical to TypeScript. So question mark dot is a safe access to methods. And then question mark is the null check. So if left side is null, use the value on the right. Otherwise, use the value on the left. Want to mention that Swift in behind the scenes has one extra trick up its sleeves, which people may or may not be interested in using. But in Swift, it's actually a dedicated optional type. So the string question mark really is just syntactic sugar. So it's not really a pointer behind the scenes. And as a result, there are two consequences of this. One, you can use it in a functional approach if you like to. So you can do, like, for instance, a text is a string question mark. You can call flat map on it and map. So to do this, chaining of functional methods. And the second one that I think might be more interesting is you can actually nest optionals. So I think you rarely need it, but if you want to, you can do a string question mark, which is an optional of string. I do not believe this can be done in any of the previous languages because they are actually just pointers behind the scenes. However, like Kotlin, Swift also has unsafe operations. So instead of bang bang, it's just a single bang in Swift's case. And instead of late init, it is you declare a variable with a bang. And I think this is like a variable that comes from Java when you call it from, or at least the platform when you call it from Kotlin. So this is the score so far. Kotlin and Swift continues to move up, Python as well, and TypeScript as well. But then Kotlin and Swift actually has ways to let you cheat now, which is why their lower bound is now half a point behind. Go does not do null safety at all, so it still stays at 1. So hopefully the scoring is starting to make more sense now. But let's continue. Let me know if you have questions. So next thing is safe array access. I mentioned before. So languages in C++, C++ really prevents you from accessing values that are outside of the bounds of an array. And that's good, right? That prevents things like buffer overflow errors. However, languages that have safe array access further requires a programmer to explicitly handle out of bounds array access. And instead of just letting a program crash on runtime. Now, I want to say that I think none of the 5 languages we're talking about does this by default, but some languages allow you to do it. There are languages like Pony that actually prevents you from doing the wrong thing, but we're not talking about that today. So Go does not have safe array access, period. So if you declare a variable of size 3 and you try to get a 10th element, this will compile just fine. Even though at runtime it will panic, right? Line 5 will cause a panic. So you run it, it panics. Like I said, none of the other languages by default actually does this either. So same thing with Python. If you try to do this, the type checker is perfectly happy to let you do it, but you crash at runtime. The nice thing about Python, though, and as with other languages, is because Python has null safety, you can convert this array access problem into a null safety problem by basically writing a function that returns an optional of type T. So if given a list of type T, so if it's within the range of the bounds, then it will return a T. Otherwise, it returns none. And if you use the safe get to access an index out of an array, what you end up with is an optional which you now, because Python is null safe, you are now required to check to make sure it's not none before you try to access the value. And if you don't do this if check here on line 9, this code will not compile. TypeScript, I will talk about, even though I know I mentioned TypeScript is very similar to Python. TypeScript solution to this is actually, I think, the cleanest of the 5 languages, even though by default it is not on. So, so let's say you've got this, array of 3 elements, you access the -1th element, it's clearly wrong. It compiles. Even if you're in strict mode, this code will compile. But then when you try to run it, you'll get, undefined is not an object. So when you access something that is out of bounds, it will return an undefined, which you cannot, do anything with. Well, I suppose you can print it, but you cannot call methods on it. However, the nice thing, what I like about TypeScript is if you use this no unchecked index access flag, if you pass it to TSC, it will actually catch that for you. It will actually know that, hey, this value might be undefined, so you cannot just call a method on it. The downside, depending on how you want to look at it, is it's any value, right? Even if this is a valid index, you have to check to make sure it's not undefined. So it depends. I think that's the reason why even by default they don't turn it on. They actually make you pass in this special flag to turn it on. But I feel like it's worth doing because the proper way to do it is to just do a question mark dot operator to make sure, if it's undefined, don't call this whole expression is just undefined. And then just, in my case, I'm just converting it to a null if it's undefined. So I actually like what TypeScript has done here. Kotlin, I will not go into detail. Again, by default, it is not safe. If you do a array dereference, or de-index, it is not safe. It will just compile but fail at runtime. However, what's nice about Kotlin is that how I say in Python, you can write your own function that does it safely. This is built into Kotlin by means of the get or null. So if you use get or null, it'll be safe. Swift, very similar to Kotlin. Actually, it's more similar to Python in that it is unsafe by default. They actually do not provide you with a safe option, but it's not too hard to write it yourself. So this actually stole from Stack Overflow, and it's actually kind of nice. You can make it an extension subscript, and the way you call it is by using words instead of just word sub -1. You do word sub and then safe :-1. And in this case, it returns an optional type that again benefits from null safety, and therefore you don't have to worry about runtime errors. Let's just breeze through this. Safe type conversion. As long as there's a type hierarchy, you are going to have type conversions. I'm talking about type conversion as in type casting here. So not value conversion. So I'm not talking about like parsing a string into an integer, which is topic 4, maybe more related to recoverable errors. So a language with safe type conversion requires programmers to account for conversion failures. And we'll show you this with Kotlin and Swift. Go doesn't really do it. So the way you should be doing type conversion in Go is by using a type switch like this. And this basically says you've got a variable named thing that's, it's just interface, anti-interface, so it's just any. It's an integer in this case. And you're saying if things type, so you switch under things type, and then you assign the casted version to this variable, which I call str because I'm only checking for string. If it is a string, then you print the uppercase version of it. And if you do it this way, then Go is actually safe. There's not much that can go wrong. However, there are lots of different ways you can do typecasting in Go that are unsafe. So, well, this is another way that is recommended you do. So the idea is again, thing, you're now saying asserting that it's a string, But then you see that you assign that the variable to a string if it type checks, but also a Boolean to indicate if it's okay. And you're supposed to check to see if the okay succeeds. And if it succeeds, then you continue treating it as though it's a string. However, it is possible for you to just say, I'm going to just ignore. So this would be the okay here. I'm just assigning it to underscore. I'm just ignoring it. And in this case, if the thing is not a string, as it's not in this case, it will assign to what Go calls a zero value for a string, which is an empty string. And this one will uppercase the empty string, and that's okay, right? Like, but it will not panic at runtime, but it also may not be what you want, right? Like if, for instance, if this is like a data, an ETL process, and there's an error, like something is not a string, you're basically filling your database with zeros or empty strings, and that may not be what you want to happen. Alternatively, you can do thing.string, again, a type assertion, but notice that you're not assigning the second Boolean this time. And in this case, it will just panic if you try to run it. Notice this is line 10. If it compiles, you run it, and line 10 results in a interface is int, not string. So you only find out at runtime. Python is, it's not really safe, but it is rarely a problem. So I mean, basically Python actually is not type conversion safe at all, but it is rarely a problem because it has this thing called type narrowing. This is similar to what in Kotlin is called smart cast. Basically, the idea is you've got a variable that could be an integer or a string, and you notice I'm doing it using a random. So randomly, like basically flip a coin. If it hits, give it an integer, otherwise a string. And the Python type checker will not let me call a string method on this because it knows that it could be an integer or a string, unless I first check to make sure that it's a string. Then within this if block, thing.upper is okay to call, right? And this is similar to Kotlin's smart cast. The problem with Python, though, because of typing is kind of added on and a lot of the type information is erased, it actually sometimes requires you to implement what is called a type guard. A type guard really is just a function that returns a Boolean. So this expression is a Boolean. However, you annotate it as a type guard. And basically what it means is if this function returns true, then the parameter, the objects in this case, can be treated as a list of strings, right? And the way you implement it is basically you iterate through all the objects in the objects array and check one by one to see if it's a string. And the way you use it really is like this. Like I said, it's just a Boolean. But if this Boolean expression resolves to true, within this if block, nums is safe to be treated as a list of strings, right? So this is how you should be doing it. However, as you can imagine, because Python is really relying on the programmer to do the type checking, you can do whatever you want, right? So you can just return true. And this basically, if you ran this, you will get a runtime exception because you're doing it wrong. And the other thing I want to mention is Python also has casting, but casting is something you should almost never do unless you really need to, because it is, again, it does nothing at all at runtime. It's kind of just a way for you to cheat the type system because you cannot get it to match. So you say, let's just force this to be some other type. TypeScript, I'm not going to go into detail because it is virtually identical to Python in terms of the feature it provides. Number of string by default, you cannot just call a string method on something that could be a number of string unless you first check to make sure that it is a string. It will sometimes force you to write. I think TypeScript gives a different name than typeguard. I forgot what it's called though. But again, you write a function that asserts that this thing is a string. Sorry, in this case, an array of strings, and then you can treat it as an array of strings. Sorry, if you first check it. But it is up to you to implement this, and you can implement it however you want. In this case, just return true, and then now it basically you end up with runtime errors. Similarly, you should not be doing cast in TypeScript. It is just a way for you to cheat the type system. It really doesn't do anything at all. So Kotlin, similarly, typically you would do smart casts, and so you really rarely have to do explicit casts, right? So again, same thing. Randomly, it could be an integer or a string. We're just giving a type of any here, and you cannot call dot uppercase on it unless you check to make sure it's a string. However, you can do explicit casts in Kotlin, and you can do it safely. And as with safe array access, the way we accomplish this is by converting the type conversion problem into a null safety problem. So thing as question mark basically just says, I want to try and cast thing to a string. If it succeeds, great, give it assign it to the variable. Otherwise, assign null to it. But this also means that this has to be a string question mark. It cannot just be a regular string. And as a result, you have to check for null before you access it. So it is safe in that sense. The only problem is, notice this is S with a question mark. You can actually also do S without a question mark, and this is an unsafe cast. So this is an option in Kotlin, which compiles but will not, may result in runtime errors. So I think moral of the story is avoid this, use the question mark variant where possible, or just use smart casts. Swift, as I mentioned before, very similar to Kotlin. You basically randomly generate either an integer or a string. If you try to treat the value as a string without first checking, it does not compile. But if you first check to make sure it's a string, then it's okay. But similarly, so Swift also has the S question mark version, which I'm not showing here, but Swift also has the unsafe version. I like Swift implementation of this better because it actually has the exclamation mark. So Swift has this nice consistent way of, if something an operator has an exclamation mark after it, that means it's unsafe. And if you're trying to write safe code, you should probably avoid those operators. But if for whatever reason you think you need it, then it's there for you to use. So this is where we at now with type conversion. Let's go next to exception safety. And exception safety is it's an interesting one because I think with language design you kind of have to, because exceptions are going to happen, and some exceptions you really cannot do anything about, right? So the idea is you take errors and you separate them into recoverable errors versus non-recoverable errors. So there are some errors that are obviously recoverable, right? Like a user providing invalid input, then you recover by rejecting the input, and you basically validate. You tell them, hey, you gave me a wrong an email address that's in the wrong format. Some are not recoverable, right? Like if your system is running, it has run out of memory, there's really not much you can do about it. And there's some that's in between, right? Like if you're trying to connect to a database and the database is down, it kind of depends. If you're writing a service that's talking to a database, then it is really a non-recoverable error because you need the database to operate. On the other hand, if you're writing something like data grip, which is basically a database client, then really it is recoverable. The right thing to do is to tell the user, hey, you're trying to connect to the database to run queries, and the database is down. So it's kind of that kind of makes exception safety a little bit of a hard problem, in that it's kind of up to the use case, the programmer, to determine what's considered recoverable and what's not. But I think of an exception safe language as a language that forces the programmer to handle all recoverable errors. Go really isn't. I'm not sure if you guys are familiar with how Go handles exceptions, but the way it does it is there's no exception throwing mechanism at all. They just have an exception type that it is up to you to return. So you can return it. So it's kind of like C returning 0 for success and a non-zero value for errors, except Go gave it a dedicated type called error. And so you basically, for instance, you've got this query unescape, which is part of the Go standard library for unescaping URL, so the percent including unescaping those. So it takes a string as an input, and it returns a string if it's successful, or an error if it is unsuccessful. But if you look at the return type, it's basically returning both, and it's up to you to check to see if error because if it's successful, then string is not nil and error is nil. Sorry, the other, if it's successful, string is not nil, error is nil. If it's unsuccessful and there's an error, then error is not nil, and string typically should be nil. But it's up to you to check to make sure. And again, you can really easily forget to handle errors, and the compiler does not really do anything to prevent you from doing that, right? So in this case, I'm saying, hey, I'm giving a bad URL, I'm trying to escape it. In this case, I believe URL becomes an empty string. This could be an error that I am not handling. So I do want to mention that the nice thing about Go is it forces you to do this underscore, so it will be obvious if you're intentionally not checking error, at least in this simple case. But sometimes, like in this case where I assign it to an error, but sorry, in this case, I'm assigning to an error, but I'm actually not checking to see if error is not nil. I'm kind of just printing it anyway. I'm printing URL2 anyway. So basically, we're in a situation where URL2 could have been from an error, and in this case it is, but it's just an empty string and it just gets printed anyway. It's just an unhandled error. Python by default not exception safe, so it has it basically has unchecked exceptions. Any function, any method can throw an exception. It's not even required to declare it in its signature. So this program compiles just fine. And when you run it, it will fail because that %c3 URL is not a valid, escaped URL. The way you can make it safer, though, is to write your own function. And in this case, you're not really converting it to a null safety problem, even though you could. But Python basically has union types, right? So you convert it to a string or an exception. So nullable is basically string or none. So in this case, it's string or exception. You just wrap it in a try. Call it, if an exception is thrown, you return the exception instead of throwing it. And the nice thing about doing it this way is now when you call safe unquote passing in, again, this bad URL, you have to assign it to a variable of type string or exception. And you have to first check to make sure it is not an exception. Or you can also check to see if it's instance string before you treat it as a string and continue. If you were to drop if you were to omit this check, then the type checker does not like it, right? It's saying, hey, unquoted or error may be an exception, and you're not taking into account the possibility that it may be an exception. Therefore, I will not allow. The type checker does not allow it. TypeScript is really the same as Python. So I'm going to breeze through this. It's called decode URI. You pass in a bad URL, it is going to throw an exception at runtime when it's bad, but then there's really the type checker does not check at all. Like it's not even noticing, like you're not required to declare exceptions. However, as with Python, because of it has this union type, you can do string or error and do return instead. Now, I'm not advocating you do this in Python and TypeScript. I'm just showing that Python and TypeScript type systems do allow you to do it. If you were to do it, your code would not be Pythonic, and unless you get your whole team to be on board with doing it this way, and keep in mind also new people joining this team is going to find this a little bit weird. So just know that I'm just saying it's possible to do, may not be the right thing to do. Yeah, so again, if you don't first check, in this case, because it's returning a string or error union type, if you don't check to make sure it is a string, you cannot treat it as a string. Kotlin, again, conceptually similar to Python and TypeScript, except that the safe version, you don't have to implement yourself. It is built in. So again, by default though, decode can throw an exception. It is not declared anyway. Compiler will be perfectly happy with it. But when you run it, you get an exception. However, Kotlin does come with this result type, which makes it more safer, right? So you can just call result.runCatching and pass in basically an expression that may throw an exception, and it will return a result of string or exception. And in order to use it, you need to account for both success case and failure case. So if it's successful, print it. If it's a failure, then print unable to decode URL. And if you were to say, hey, I don't feel like calling one of these lines, I only want to handle a success case or just a failure case, the compiler does not allow it. Result is part of Kotlin standard library. I think it's relatively new, but it's there. But if you don't like that, and I heard that actually Kotlin's result isn't that feature rich. There's also Arrow, and I think there are other third-party libraries that provide similar functionality. Swift is actually really nice in that it is completely exception safe, unless you use one of those exclamation point operators. But Swift exceptions are checked, and I know there's a debate whether unchecked or checked is better. But Swift went with the checked approach, which means, for instance, if you write a decode URI function, and it can throw an exception, you have to declare it with the throws at the end here. And so you're basically indicating that this function. So at Swift at compile time, you know if a function will throw an exception or not. And when you're calling it, so when you declare it, and then if your function actually throws an exception within it, but you do not declare it, it is a compile failure, right? So the compiler doesn't let you do that. And then when you call it, you are required to handle the exception. So for first line, I'm just trying to call decode URI without accounting for the fact that I could throw an exception. The compiler doesn't allow it. You have to do one of two things. Well, maybe that may be a third thing, but I'm showing you two here, where you have to either call your try question mark, which is where you're converting the exception safety problem into a null safety problem. So it basically means if it doesn't throw an exception, assign a value to URL2. If it throws an exception, just assign null to URL2. And then now you need to do a null safe access to URL2. Or you can just do this do catch approach, which is, I think you're probably familiar with it in Kotlin as a try catch, but it basically says, do this, you try to do a decode URI. If it's successful, assign it to URL3. Otherwise, if an exception happens at all, just assign it to this random, literal value. However, like I said, Swift does offer the exclamation point version of try, and this is the unsafe version. So if you do this, you're basically saying, trust me, I know that this exception, even though it's declared to throw an exception, never will in reality, except in this case, you will get a runtime exception. So if you want to write safe Swift, don't use this, is the moral of the story here. Swift also offers the result type. And I like that both of Swift's options are safe, but I kind of don't like that they give you two options at all. I kind of wish it was only one. But anyway, I'm going to show you the second option. Again, this is built into the language. So there's a result type, and you can wrap a function that throws an exception in a result, and the result will be an error if the exception did get thrown. Otherwise, it will just be whatever the return type is of the function. And it because Swift has exhaustiveness matching, which we'll talk about next, you can just wrap this in a switch statement, and you have to handle both success and failure cases. And if you fail to handle one of them, like you're saying, hey, I only care about a success case, you get a Swift compile error saying that switch must be exhaustive. And yeah, I'm not sure if this is the complete error. I thought it was, but Swift I thought was generally pretty good about showing you what cases you're not handling. So I may have to revisit this. But again, you are required to handle successes and failures when you're using the result type. This is a score now. So basically, Swift and Kotlin has moved further ahead now. And Go basically stays where it is. Python and TypeScript moved ahead a little bit, but like I said, the lower bound will be 0. So exhaustiveness checking is an interesting topic that I want to go into type theory a little bit. And I guess the idea is you can think of a computer program as a series of state transitions. And when you're doing exhaustiveness matching, you're basically saying that the programmer needs to account for all possible states when they're moving forward. And like the idea here is, so I'm going to type theory a little bit, in that the idea is there are, in algebraic data types, I'm not sure how familiar you guys are with it, but I'll just go into it. I don't really know the details either, but the idea is there are two kinds of types, right? There are what's called sum types and product types. I'll go into product types first. So product types is when, and these are ways you compose types into, composite types. So a product type is when you take the component types and you AND them together. So an example would be, for instance, if you declare either a struct or a data class of, say, a person, where a person is a first name and a last name and a date of birth, for instance, right? So a person is a string and a date. So that is a product type. And I think we're all familiar with it in the form of data classes, in Kotlin, structs, in Swift, in Go, that's structs, and in TypeScript, I guess they're classes. The other type is a sum type, which are when you take the component types and you OR them together. And we've seen examples of this. So like nullable types are either a string or null, or the result type is either a type, like a type T, or exception, right? And you can also declare this, you can also declare your own kinds of this, like Kotlin enums, like a direction is north or south or east or west. So it cannot be both. It can be just, one, it's an exclusive OR of one of those values. Or it could also be, again, in Kotlin, sealed interface, right? So where it could be, you can declare a sealed interface and you declare a fixed number of concrete implementations of it, and you know that the value is going to be one of those types. So exhaustiveness checking takes union types, and it further basically forces you to, if you've got a variable of one of those types, account for all the possible cases. Because, for instance, if you're in enum, you know at compile time that direction has to be north, south, east, or west. You cannot add more of those to it without without recompiling. And so you can check to make sure, hey, if for instance, you're saying, hey, if it's north, do this, but then the compiler is saying, okay, I know what to do if it's north, but what if it's south, east, or west, right? So the compiler is basically forcing you to account for all possible states before continuing. And the reason I think this is so important is, it's useful for things like enums, but if you think about it, things like null safety, exception safety, and everything before that kind of basically dissolves into a null safety problem, is only possible because of exhaustiveness matching. They're all basically classes of exhaustiveness matching problems. And the reason that Go doesn't do any of those things is because Go does not do exhaustiveness matching. And again, they were trying to keep the language simple is what they say, but I think as a result, they basically lose out on this. Any questions? I know that there was a lot. All right, I'm going to go into this. So I want to mention something, that Go actually does have some types in the form of sealed interfaces, and a sealed interface is an interface with a private method. I didn't go into this. I don't know how familiar you guys are with Go, but in Go you declare an interface like this, so a type account status is an interface, and anything that starts with a lowercase is private. So is status, because of the lowercase I, is a private method. If you wanted to make it public, you make it an uppercase I. So if you made it uppercase, it will be public. So in this case, I'm declaring an interface account status that has a private method, and I'm declaring two types that implement this interface. And because it is a private method, I know that active and inactive are, in the whole world of Go, the only two possible implementations of account status. And if I see account status, I know it has to be one of those two. It can be anything else. You cannot add to it outside the package. which means in theory, at least at compile time, it should be possible for you to know that given you've got this account status type, that if you account for the active case and the inactive case, you have accounted for all possible states. However, the Go compiler is not able to make that inference. And so it's saying that you still need a return at the end, or you could also do a default case, but it doesn't do exhaustiveness matching for you. It's basically what I'm trying to demonstrate here. Right. So yeah, so Go doesn't do it, which is partly why it doesn't do null safety and all those other things. The same example in Python would look like this, where you've got an enum class, active and inactive are two possible values. There are only two possible values. And so when you do a do work, and match, by the way, is new in 3.10. So before 3.10, you don't have the match keyword. So Python does not have exhaustiveness matching until 3.10 really. But doing the match, because you've accounted for active and inactive, the Python type checker actually knows that, okay, this function is okay, you've accounted for all possible case. However, if you were to add a third enum value to it and you run the type checker again, it will actually tell you, wait, you are not exhaustively handling all values, and will tell you exactly which case you're not considering. Or like I said, it also gives you this option of saying, if you don't really care about exhaustiveness handling, then you can just do the case underscore, which is just a default case. TypeScript, really very similar to Python. It will just, in this case, it's done using the switch statement. And a switch, if you're accounting for all cases, it's happy with it. If you add a new case and then you do not add it to the switch, then it will know that, hey, you're not being exhaustive. The compiler will complain. Kotlin's when, I'm sure you guys are familiar with this, same thing, right? You declare an enum, active, inactive. If you handle both cases, you're good. Compiler's happy. If you add a third case without updating the when, compiler's no longer happy. Now I want to mention real quick here. Notice that when, and there is a status of it's just a single status, right? I'm not doing a pair or triple or anything here, because if I were to try and do that, Kotlin or Python or TypeScript no longer does exhaustiveness matching, which is where Swift actually shines here, right? So Swift, in this case, I'm showing you that Swift, I'm declaring two enum types, so a status of active, inactive, and membership or basic premium. In Swift, I can actually do a switch on a pair of status and membership. And the Swift compiler, which is part of the reason why the Swift compiler is slower than everything else, is because it will actually do this check for you. It will make sure that, you can imagine how I'm only showing you two, but if there were three enums and instead of just two values each, it's like 5 values each, it'll be 5 times 5 times 5. It can basically explode combinatorially, and it's crazy, but Swift will do the check for you. And it will even, so if you remove one case, it no longer compiles. It's even smart enough to figure out that, hey, like basic and premium, we are just doing the same value. You can just do an underscore there, and it will do the analysis for you and make sure that exhaustiveness checking is done accurately. So this is where we are. I'm going to try and breeze through because I think I'm running out of time here. Let's talk about encapsulation again. Encapsulation, it's unclear to me that it is really part of the type system, but I want to include it here because it is a feature of a language that allows you to prevent errors at compile time. So the idea of encapsulation is that program state is rarely relevant globally to a program. So they usually apply only to a limited scope, like to a specific object or whatever, or module. And so a language that enforces encapsulation basically allows the programmers to declare that this variable should only be relevant to a specific scope, and it can be done by keywords like private, protected, internal. But then the compiler then basically limits, basically it does the checking for you, right? If you declare a variable as private and you try to use it outside of the class, then the compiler does not let you do that. And this basically helps you write safer program or at least find bugs more easily if they do occur. And Go does do this. Go basically, like I said, if you have a variable that starts with a lowercase, as is the case for this count here, then it is a private variable. It is only valid within this package counter. And so I've declared a struct name counter that has a count in it, and I declared two methods on counter. So count basically just returns the current count, and then increments the count, right? And because I made count private, I basically can not accidentally try to change the value. For in this case, I'm trying to demonstrate that a counter, really the count should never be less than 0. So, you cannot accidentally set it to a value that's less than 0 outside of counter. And if it does happen where you find a case where you've got a count that's negative, you know that it all happened within the count module, and you can find a bug there. And in this case, this can happen when you overflow. But yeah, the point is just to show that you cannot accidentally, like, if there is a bug, it is within that module. You don't have to worry about some other module messing with your data. Python is actually kind of interesting in that the Pywrite type checker, even though I think the Python PEP is what it's called, basically the specs, says that underscore is really just a recommendation, and they do not recommend enforcing it. The Pywrite type checker actually enforces it when you use it in strict mode. So if in this case, it's the same example. I declared a variable called underscore count that is private. And then again, two methods to access and increment. If I try to access mutate underscore count from outside of counter, again, Python is really saying you should be allowed to do that, but Pywrite actually will flag it as an error, which I think is kind of a nice thing, even though I know the Python language kind of doesn't really kind of frowns upon that, because the idea is you should trust your clients to do whatever they want. But yeah. TypeScript, and this I think is actually from JavaScript. Same thing. I'm going to breeze through this a little bit, but if you name a variable with a hash count, it makes it private. You cannot access it from the outside. Kotlin, I think you guys are familiar with this. In this case, I only have a method to increment because I declared count as a mutable variable, but with a private setter. So it basically by default has a public getter. And so you cannot try to mutate it from the outside. Same thing, if the value becomes negative, you know that you had implemented a bug in the counter itself, and it's not from somewhere outside. Swift, almost exactly the same as Kotlin, except you do the private set this way, but conceptually you have a increment function. One thing I do like about Swift is that if you have a function that mutates state, you need to indicate it with a mutating. So I think they borrowed this from Rust. But yeah, conceptually the same. So let's talk about, finally, I'm going to breeze through this a little bit. Immutability is the last thing. And I think mutability, I feel, is a source of many bugs, especially, especially in parallel environments. And so languages that enforce immutability, basically, as the programmer, you have to indicate if data is mutable or immutable, and then the compiler checks that you do not mutate immutable data. Go really doesn't do this. So you kind of have to rely on the uppercase, lowercase, public, private thing. And you basically, if something is immutable, you have to declare it private, and just be sure to not mutate it within your package. But at least you know that outside of your package, no one can possibly mutate a value. So so if you look at this example, it's a circle, you give it a radius, and then it calculates, you have an area method that basically just does pi r squared. Right? So Go really doesn't do, like I say, it doesn't really do immutability. So you can do a unit circle is a circle of radius 1. And then you print it, right? Like, so the radius is this and the area is that. If you change the radius to 2, let me see if actually this would work just fine. But if you were to cache it, right? If you were to cache the area because you figured, hey, it's supposed to be immutable, this would not work. So that was a bad example, but I think my point is you can, however, by declaring it with a lowercase, so radius with a lowercase r here, makes it private and therefore inaccessible from the outside, and you just have to basically promise not to mutate it from within your own package, and then and this one's okay, right? So you basically have instead of having the radius be accessed directly as a variable, you just have to declare a getter and accessor method that returns r. So Go does have some form of immutability, but it's up to you to implement it yourself. And honestly, as someone who's writing a lot of Go the last 2 years, it's actually really cumbersome to try and do this in Go. It just like the support just isn't there, unlike languages like Kotlin that encourages immutability. But it's there if you really want it. Go does, however, have consts, which are constants, right? And constants can only be basic types like integers, strings. And so math.py is a const. And so basically the idea is, okay, so unit circle.r, I'm demonstrating here that because it's private, you cannot modify it. But math.py is a const and you cannot modify it because it's a const. Python, really, I think at the end of the day, they provide you with this concept of a data class that's frozen. So it basically encourages immutability. And I'm showing you where, okay, this class is supposedly immutable. So you've got a radius and you cannot change it. And then you can do a cache property of area that returns, pi r squared. And that's nice. If you were to try and modify it, the type checker doesn't allow you. But because it's Python, you can actually do something like this, and you are basically mutating state at this point. And again, Python really just is very much a language that just trusts your clients to do the right thing. If they want to, let them do it. They will be responsible. And this is where, that's just Python's philosophy, though. The thing that I find a little bit annoying with Python, though, is that there's nothing immutable at all. So for instance, even mathpy, and this is the mathpy that comes from the Python standard library, you can actually assign it to something different, right? So it comes by default as 3.14, but you can set it to 0. And now when you call circle.area, it actually gives you 0 because it's using your definition of pi. Yeah, so Python's immutability story isn't that great. It kind of encourages it. That's frozen, that basically you're communicating to your users that, hey, you probably should not change the values in here, but if you really want to, there's nothing I can do about it. TypeScript has read-only, and TypeScript's immutability is actually pretty good, right? And it comes from JavaScript. I think read-only basically makes it immutable. And so now you can, if you wanted to cache this, I'm not doing it, but you could. And it works just fine. If you try to mutate a read-only variable, compiler doesn't allow it. If you try to, in this case, math.py is a const, you cannot modify it because it's a constant. Kotlin, I think you guys are familiar, is, you use val. Kotlin and Swift really encourages immutability, or at least it kind of, where other languages like TypeScript, you kind of have to do extra work, right? Like you make it read-only to make it read-only, or like in Java, for instance, you have to add an extra keyword like final to make it immutable. Kotlin and even Scala and Swift basically treats immutable and mutable variables the same, in the sense that, it's really just you type the same, type 3 characters to declare a variable that's mutable or immutable. So it's not you're typing extra characters just to make it immutable. And it's val versus var in Kotlin. It's let versus var in Swift. And in this case, I declared a radius that's immutable. And I've also declared a lazily initialized variable called area. And in this case, this just means you don't have to calculate it if you don't need the area. That is also immutable, and it's based on radius. If you try to modify it, the Kotlin compiler doesn't let you do it. You cannot override pi like you can in Python. Swift, like I said, it's let instead of val, but otherwise, same concept. Right? You cannot override constants, you cannot override immutable variables. And this is where we are now at the end. So we're at the end now. I'm sorry, I kind of went a little bit over. But let's talk about basically the conclusion, right? Like, so what does all of this mean in terms of helping you write safe software? So the way I like to think about it is, think about if your code compiles or type checks, what are the things you do not have to worry about anymore? I think I like Ian. I think you said this. I forgot a few months ago where I think you described like strong typing as the ultimate shift left, or something like that, right? Like the idea is that you are catching errors as early as possible. So in this case, if your code compiles, these are areas you do not have to worry about anymore. So Go, as you can see, the type system is fairly weak, right? So if the code compiles, really, like I said, memory leak and buffer overflows are, are kind of like basically all modern languages do it. So really, type mismatch is the only real guarantee that Go provides. The yellow and the orange are more like you could write your program in such a way that these problems go away, but not necessarily. And the rates are basically like, no matter what you do, these are the only way to prevent this from happening is by being careful or writing unit tests, because the type system isn't going to catch this for you. Contrast this with Python. Again, it's not that great because of the optional typing part of it. So, but there's a lot more yellow and oranges in Python and TypeScript. But then as you go into Kotlin, you start seeing more greens, right? Like again, type mismatch is guaranteed not to be there. Null pointer dereference and type conversion failures they're not guaranteed. And Senthil, I'm actually glad you brought up your problem today, because it's we're saying that null pointer dereference is light green, as in it's for the most part not going to be there, but it can still be there either when you're doing Java interrupt or if you're using the bang bang operator or late init. But at least if as long as you avoid those features, these are not problems really. And these are like, you can write your program safely to avoid this. Again, data races, arithmetic errors. Like I said, these are classes of problems that no type checker will catch. At least with data race, Rust and Pony does, but a lot of this really, nothing is really catching those. So those are the problems you still have to worry about. You still have to write tests to handle this. You still have to be careful to avoid those classes of errors, but your compiler is for the most part taking care of these guys for you. And Swift is, it goes one step further. Again, I consider Swift's error handling a little bit better, which is why it's yellowish green, whereas Kotlin, it's exceptions can still happen uncaught relatively easily. So finally, I guess I want to talk about, let's say you are using, so if we're using Kotlin for the most part, type checking is going to be pretty good. But this is where I want to talk about how do you handle the reds and the orange categories. And you have a few options, right? So you can enable stricter type checking. And this is really for languages like Python and TypeScript, where the compiler actually has many flags that you can configure. I feel like Kotlin's by default is fairly strict. You can probably turn on additional flags to catch more errors, but you can't really do that much there. You can use code generation. And I think this is more of a Go thing. Go actually comes with Go generate that basically allows you to generate code that is safer. You can do additional pre-compile checks, and I'm talking about things like additional static analysis tools and whatnot. And finally, automated testing, right? So if whatever your compiler isn't doing for you, you have to write tests like unit tests or integration tests to catch those things. So like I said, stricter type checking is mostly a Python and TypeScript thing. These additional flags you can give it to do more type checking for you. Like I say, code generation is actually kind of useful if you're in Go, and Go actually has a bunch of Go generate tools that are built into the language that basically allows you to catch more problems that a type checker doesn't really handle. And additional pre-compile checks, we're talking about things like linters, static analysis tool. I mentioned before that Go doesn't really do exhaustiveness matching. So this guy actually wrote something called Go SumTypes, which adds it. So, but unfortunately, that also means that you have to add another tool as part of your build system. And SwiftLint, for instance, SwiftLint is actually pretty nice. I haven't looked at the Kotlin one. I bet the Kotlin one is pretty nice as well. But for instance, SwiftLint, you can actually say any of these S exclamation mark or exclamation mark operators. They will actually like fail your build if you use those. And that will actually turn down the yellowish green stuff from my previous slide into a deeper green. And finally, I consider this like literally the other things I just talked about, the last 3 slides are nice. But at the end of the day, if your type checker isn't doing something for you, you kind of just have to write unit tests to make sure that those errors are not happening, right? So in Go, like always test nil input to a function to make sure that it is, but it's up to you to do it, right? The compiler isn't going to catch it if you don't test the nil case. Always mock error conditions, and then do fast or property-based testing to basically give it random values to probabilistically find, null pointer exceptions or whatnot. I think that's it. So yeah, I know that was a lot. Any questions?
Would you mind just going back? Did you have the final scores slide? That was
Oh,
pretty
yeah.
neat. It's interesting to see where everything
Yeah,
landed.
absolutely. This, right?
Yeah. Well, pretty cool.
Yeah. So again, Kotlin and Swift are basically at 7.5. It's pretty much full marks in terms of the upper bounds. You can, at least of the things that I'm covering here, Swift and Kotlin does pretty much everything. I don't even remember where they lost the half points. I think Swift and Kotlin actually loses them in different places. I think with Kotlin, it's exception safety, and Swift, I think, is the safe array access. It doesn't do it as well. But then the reason this is low is really because of the try exclamation marks and the ask exclamation marks, where it's like, by default they don't really let you do bad things, but they give you options that I think even documentation, they encourage you not to do it. But I think it's like sometimes it's just necessary to solve certain classes of problems.
Great. Any other questions? Questions for Jack? Or
I know there's a lot of material. I'm sorry. So.
Oh, don't be sorry.
Yeah,
This is
that was
great.
pretty good, informative. Do you have like a reference to the slides, or like are you gonna planning on posting it anywhere?
I can share it. Yeah, it is hosted. It is hosted. I will share a link at least to chat after this, and then Ian, if you want to, I don't know if there's a way to distribute it, or I guess I can post it as a link on the meetup as
That
well.
would be perfect. Yeah, on the event page for
Yep.
today's event, just as a comment there, and everybody can get to it.
Yep.
That'd be great. Excellent. Well, any other questions before we stop the recording here as well? Okay. Well, we'll wrap it up. Thank you so much, Jack. Really appreciate it. Great talk and good information, and good to see that Kotlin is, up there and trying to help us create safe code.
Yeah.
That's one of the reasons I like it. So good stuff. And Kotlin and Swift are such similar languages, so it's interesting to see them kind of just side by side for the most part. And a lot of these, obviously some different platforms, so different design, trade-offs here and there, but a lot of similar inspirations. So yeah, thank you so much, Jack, for the presentation, and I really appreciate it.
Thank you. Actually, I wanted to mention one thing, which is the thing you covered, I think, 2 months ago. Which is like, I'm only really covering the surface of strong typing too, right? Because actually Kotlin, for instance, takes it further. Like, remember the value type thing you're covering, which I'm not even talking about here. So actually, like, Kotlin actually allows you to define more granular type things. So it's even more control, preventing even more classes of bugs. But that's where we're talking about details that I'm not really covering here. So really, it's actually a little bit more than that too.
Yeah, with the inline classes. Yeah, kind of an efficient answer to primitive obsession, and just sort of encouraging you to just author more type safe code in general.
Yep.
Cool. Excellent.
Cool. Thanks,
All
guys.
right. Thank you, Jack.
All right, I'm going to stop sharing.